In this lesson, we're going to revisit a concept that we talked about in the previous unit, and that's called the scaling principle for area. And what it says is if two figures are similar, then the ratio of their areas is equal to the ratio of their sides squared. So we did this in the last unit. We found the scale factor for sides, and then we squared it to get the corresponding scale factor for areas. But it's not only equal to the ratio of their sides squared, it can be any pair of corresponding lengths. So those could be any dimensions in the similar figures. If you look down at the two examples here we have side lengths, but over here we just have distances across the same part of the two images. It could also be, if it's a dilation, it could be the ratio of the distance from the center of dilation. So there's lots of different ratios we can choose, but the theory is the same because the scale factor will be the same in all those cases. So you square the scale factor to get the scaling factor for the area. So in these examples, they're pretty simple. Find the ratio of the areas of each pair of similar figures. Here we have 2 and 5. So if this is going to be image 1 and image 2, then we know the scale factor, if I go from 2 to 1, is 5 over 2. And that means the scale factor of the areas, area 2 over area 1, is going to be 5 over 2 squared, which ends up being 25 over 4. The same thing happens with this image. We don't have a side length, but we do have a distance across, so any corresponding measurement will work. If this is image 2 and this is image 1, then the scale factor, area 2 over area 1, is going to be 2 over 3 squared. So that ends up being 4 over 9. Depending on the direction you go, again, image number 2 is smaller than image number 1, so you would expect the scale factor to be smaller, less than 1. So here's how we use this concept in a problem. You might get a problem where you don't have the two dimensions to calculate the area. Here we have two rectangles. I'm missing one dimension from each, so I couldn't do a direct area calculation, but it says they are similar, and I know the area of rectangle A. He's 88 millimeters cubed, or squared. So I want to get the area of B. Well, the area of B is going to be, area of B over area of A is going to be the scale factor going from B to A, so 30 over 16, and I'm going to square it. So if I want to get from one to the other, I know area A is 88, so the area of B over 88 is going to be equal to, when I square the 30 and the 16, 30 squared is going to be 900, and 16 squared, I gotta remember what that is. Alright, 16 squared is 256. So you can cross multiply 256 times area of B, and that's equal to 900 times 88, and then you would divide by 256 and you end up with the area of B is going to be 309.375. It should make sense that the area of B is larger than the area of A, and that's square millimeters. The other way you could have done this is just multiplied the area of A by the scale factor squared instead of doing the cross multiplication. Either way you'll get the same answer. But the key is you find the scale factor, 30 over 16, and square it, and then you multiply that by the area. So for example 3, I want to see if you guys can set it up on your own. E and F are similar and drawn to scale. If, well, I don't think it matters because we're given the dimensions anyway. If the area of E is 120 millimeters squared, what's going to be the area of F? So look at the two images. I guess the drawn to scale part means you can determine which one's bigger, which one's smaller. But be careful, please. This is 2.4 centimeters. This is 15 millimeters. So you need to convert to millimeters since the area is in millimeters squared. So instead of 2.54 or 2.4 centimeters, it's going to be 24 millimeters. So just write that right over the other one. And then do the conversion. Find the scale factor, square it, and multiply it by the 120. And we will see what you get in class. So when objects are similar, the scale factor, they have the same scale factor for every corresponding dimension. And that's when you would square the scale factor to get the scale for the areas. But sometimes we can stretch an object by different dimensions or different amounts horizontally and vertically. And horizontally had a typo there, so I fixed that because that's going to bother me. So if we look at the little area of, if we look at the square here, it's 1 by 1. And if we scale it horizontally, the vertical height doesn't change, but we scale it horizontally by 3, and just the horizontal height changes by 3. And then let's say we scale the vertical height by 5. Well, the original area, with the square on the left, is 1 by 1, so that's 1 unit squared. The area of the big rectangle is going to be 3 by 5, so that's going to be 15. Well, how did we get the 15? If I want to use some kind of a scaling factor to do this, and I want to multiply this area by a number to get the final area, well, it's pretty evident that I got to multiply by 15. So we get the 15 from the two different scale factors, the 3 and the 5. So we're not going to square anything this time. The scale factor for the areas, I'll just write it out. The scale factor for the areas is going to be the product, 3 times 5. So we're going to multiply the linear factors. And you do this when it's not a dilation, where you're scaling by different values in the two different directions. So if you think about what we do when things are similar, we're still multiplying by the two factors. It just happens to be that the factors are the same. So the linear factors. And then when they're different, you have to use the two different values. So we'll finish this up with this last example. The small star has an area of 5, and the large star is obtained from the small star by stretching a factor of 2 in the horizontal direction and a factor of 3 in the vertical. So it's 2 this way and 3 this way. That means the scale factor for the areas, we're not going to square anything. It's going to be 2 times 3. So the bigger area, if this is A2 over A1, this is going to be A2, A1. That's going to be equal to 2 times 3. A2 over A1 is equal to 6. So A2 over 5 is equal to 6. You cross multiply, and the second star has an area of 30. So we'll work more on this in class. This seems to be one of the biggest things that kids forget about when it comes time to take the test. So you got to remember, when I have similar objects, you square the scale factor. When you have an image that's stretched by two different dimensions, you just multiply them together, and that's how you find, that's how you're able to get areas without knowing all the formulas. So we'll do more of this practice in class.